was about 205,000 people. It's a little bit smaller than University of Michigan's stadium, which is a huge one, and I'm about 5 minutes walk from that iconic building, and I'm in this from Canada. So our labs are in the basement and the faculty office. So the purpose of showing this is that if you happen to be near Ohio, please let me know, and you are most welcome to visit. With that, I'm going to start with this slide, which you may have seen, some of you may have seen last year as well. I find it very relevant postgraduate research. It's successful, is called RDAD, and R stands for read. So we have to read a lot to do graduate research or postgraduate research these days. Good thing is that you can read a lot just from your smartphone. So things are very readily available. So convenience-wise, it's good. The inconvenience is you have to start reading. Economics-wise, reading can be very passive. If you are reading more in depth, we may read just the abstract or summary, and we think that we understand. That type of reading is not going to ultimately help you in the research work. And importantly, even more importantly, while we read, we must think. In fact, absorb. You're not going to absorb everything in first reading. In fact, for me, I usually start getting things after second and third. So it depends on the topic, how familiar you are. So thinking is important, and discussion is extremely particularly আমাদের culture, আমি যখন student ছিলাম long back ago, তখন culture ছিল just read, absorb yourself and go to examine the show or do your own research and don't discuss it. I don't know the culture now, but in Western countries, particularly in America, discussion is a key component of postgraduate. Because they have figured out through the discussion, only through the discussion, you can not only expose your weak, but you can learn from others. So let's say if you are looking at, take an example of, say, absorption of a gas molecule on material surface. So we have some idea about what the surface of the material is, depending on the bonding, economic distribution, etc., and some surface properties. Chemists are actually trained very different from a molecular point of view, the molecular interaction of the actual molecule that is getting absorbed on the surface. So they have a very different perspective. And the physicists will look at the electronic interaction of that molecule surface. You can see that people coming from different backgrounds have very different idea of thinking about the same thing. So you can see, if these people are discussing the same problem, it's only dependent. So it's important, very important. And while discussing, you have to be active participant to ask questions, why and why not. So don't be just passive. And you can do all of this, but at the end of the day, you have to do for it. So that's final one, and an important one, because many times you have seen very intelligent students. But with intelligence comes laziness too, not only. So, it's statistically shown that intelligent students are one of the lazy ones. Because they think that they're too smart, so they don't have to work hard. So it is the hard work that can replace your deficiency in intelligence. So if you're not one of the super smart people, intelligent, you can make up. And in many cases, you can actually exceed the so-called smart by doing hard work. So that is also important. So this is why I put up that lecture topic wise you have probably since already first uncovered some of the fundamentals of point defects and how it is relevant to students' research and why it is important. Then I'll talk about how to create point defects and create it in a very controlled and designed way that actually control the amount of defect you want to get. And depending on the type of property that you're looking for or the application you're looking for, you have to actually sometimes design specific amount of defect in do that by a sort of controlled atmosphere processing. It's very important for ceramic research, particularly for people who are doing electronic ceramics. They have no other choice but to do this controlled introduction of point defects in ceramics. The reason being that from an functional property point of view, like electronic properties and magnetic properties and optical, pure stoichiometric ceramic materials are usually dull and boring. All you can do is make coffee, some sanitary wire and something. But if you really want to introduce functional properties, you have to introduce quote-unquote junk, meaning defects and duration. So that has an advantage, that's why ceramic industries are not one of this semiconductor type industries together. Really follow the protocol that has to be very pure and you don't want them to use dirt and so on. But in ceramic lab state, which is not scientifically correct, but if junk is going to make your ceramic interesting, then why do you care about what your students carry in the lab? Which is, to some degree it's true, but not absolutely. Then I'll move on to a sort of related topic of the so-called application of AC electrical measurement as opposed to DC measurement. So for example, if this is myself, and if I put two contacts, electrical contacts, and measure electrical conductivity of that, I can use Ohm's law, apply voltage, measure current, apply Ohm's law, get resistance value for the entire sample, and then by looking at the electrical contact area, the distance to the electrode, I can convert it to conductivity, inverse the resistivity, etc. But if this is, let's say, a two-phase interface, composite, and if I'm interested in finding out what is the conductivity that has been contributed by each of the states, that DC electrical measurement cannot answer that question. Or if this is a polycrystalline material that has grain and grain boundaries, etc. And if I'm interested in answering the question that of the overall total conductivity, what fraction is coming from the grain boundary? And in many of the ceramic material variations, so you can minimize the number of grain boundaries by making the grains bigger, for example. And DC electrical measurement will not answer. Or if this conductivity is coming from two different sources, let's say electronic nature as well as ionic conductivity. And the DC measurement will tell you, well, that's your total conductivity of the sample. My time, if I say, okay, I want to find out what fraction of the conductivity is coming from ionic diffusion through the material versus electron transporting through the material. And this is important because in many of the devices, these days people are looking for mixed ionic electronic balance. so-called mean. So in that case, you want to know what fraction is coming from ionic conductivity, what fraction is coming from electronic conductivity. With DC measurement will not answer. And you will see that if you do the AC electrical method, and by using so-called intelligent or let's say thoughtful electrical circuit model, you can actually figure out this fractional properties coming from different phases or grain boundaries, electronic versus ionic, etc. But in that case, as we will see later on, that you will have to be very deliberate about what equivalent circuit you should use. If you will see that you can do the AC electrical measurement of your sample, and you have multiple choice for what circuit model you're going to use to fit the data. Well, obviously, your sample will be true to only one of those circuit models. It cannot be different interpretation. And this is where the material scientists can contribute, because you can actually verify the validity of the circuit model that you're using with the data by tweaking, by changing your sample preparation, electrical contact material, etc. So that's something that hopefully I'll be able to communicate to you, and I'll communicate to you by taking different examples. So I'll take examples from suppose semiconductor resistive and for sensors, superionic conductors, as they are applied to sensing, batteries, and fuel cells. Mixed ionic electron conductor, I'm showing one example. As an electrode material, we use solid and conductor. This is where this MEAC is important, because historically it dealt with electrochemical cells, like batteries and fuel cells and a lot of other electrochemical devices, who traditionally use electrolyte as a liquid. There are advantages and disadvantages of using liquid electrolyte. In fact, many of the batteries operating these days are liquid electrolyte. What is the advantage? Liquid electrolyte will give you good ionic, with your ion much more mobile in the liquid medium than in the solid. Some of the disadvantages that you have to, when you're designing a device, you have to think about creating a component that can hold the liquid. And if there is a leakage of anything, so that can be an issue, and liquid is going to be usually very reactive. So many of the issues are, how to contain the liquid in an electrolyte. Are they going to be leak related to other chemical reactions to the cathode and anode? What would be an advantage of having a solid electrolyte? So if you can replace the electrolyte component, the liquid, with a solid component, that is so-called the superionic conductor. So there are electrical conductors that conduct almost like liquid, ionic species at room temperature over 150 degrees Celsius. So if that's the case, then you can replace that liquid with solid. So advantage of being don't have to portfolio of containing it. The other advantage is that we integrate your device, like the battery and fuel cell or any other electrochemical cell, with integrated circuit technology. It would be an advantage if you can make the device two-dimensional, like using films. So if you're using solid, all solid, electrolyte, cathode, anode, everything solid, you can use thin film technology or some of the floating technology that create. With the liquid, you cannot easily do that, then you have to still think about containing that liquid. So there are advantages and disadvantages. I'm not going to discourage it because most of the products are still liquid. So we have this own advantage of this. And then finally, I will take an example using the species electrical management model. You're determining its behavior using sort of nanowire that research people are using one-dimensional nanowire in analysis. So that's the plan. Before I get to the main topic, I wanted to actually tell you why, let's see, a bit more. Why is it important to introduce point defects and salts, particularly in ceramics? I'm going to take an example of a simple one, like something like titanium dioxide. I have to be careful here. So if you take something like titanium dioxide, stoichiometric, pure ionic. You know in this material, the titanium are tetravalent. So you basically have a solid with titanium oxygen bond, and your titanium is tetravalent, 4+. Okay, how can the electron move to that solid? Well, if it's, excitation across the band gap is quite high, anywhere from 3 to 3.4 electron volt. So let's take a number of 3.2 electron volts. And do you have a sense of what an electron volt is? How big is that in 3.2 electron volt? So, see, room temperature. (300 Kelvin). At 300 Kelvin, there's, I think, 25 milli-electron volts. Milli. Now, to overcome 3.2 electron volt band gap, how much energy? Obviously, room temperature is not going to be dependent on. And it's a thermally activated process, so you can calculate probably will have to go to very high temperature. So that's not a very viable mechanism of introducing electrical current in that. The other option that you can get electron hopping between your cations. So titanium sitting here, another titanium there. If you can help electron hop between those two, that would be another viable option to which electron can sort of hop from cation to cation and from that level. So if you know something about energetics, there is no energetic incentive for an electron to hop from a titanium 4+ to a neighboring titanium 4+. It would be energetically too prohibitive. Okay? So that's not, and because of that, if you can introduce point defect in that material, you see that will be possible. So for example, if you create a non-stoichiometric diode, so titanium 4-2 -X, non-stoichiometric. Oops. So you can see that for each titanium, there are less than 2 oxygens. It's 4-2 -X. And X is something that you can actually tune by this so-called controlled atmosphere furnace processing. That's how this controlled atmosphere processing comes in. you can tune that X. But if you have this material, now in this material, not all of the titanium, most of them is still 4+. But you can see some of the titanium will have to be 3+ to compensate for this deficiency in oxygen. So as opposed to that material, where all titanium is 4+, in this material you will have a mixture of titanium 4+ and titanium 3+. And when you create that kind of material with multivalent cation, now you can see that, now you can get electron hopping between the titanium 4+ and the titanium 3+. And if you look at the locally at the bond, where you have titanium 4+ sitting here, titanium 3+ sitting here, when an electron hops, this one becomes titanium 4+ and this one becomes titanium 3+. So locally, if you look at the V energy, we think about in terms of thermodynamics. You can see that change in Gibbs energy is not going to be much. Locally, it's still a bond of titanium 3+ in the neighborhood of the titanium 4. So electron hopping now becomes energetically very, very possible. And so, while this material is an insulator, this is an N-type semiconductor. So by this controlled atmosphere processing, you're basically converting an electrical insulator into a semiconductor. Now, if you're silicon and germanium like small band gap, it's a different way of making semiconductors. High band gap semiconductor. What is the advantage of high band gap semiconductor? It would be temperature instability. So while silicon and germanium, for example, is always prone to oxidation, particularly at elevated temperature, that you always have to worry about both during processing and application, that you don't want to oxidize your silicon or germanium, gallium arsenide, and so on. You don't have to worry about oxidation of titanium. It's already an oxide. So that's not a problem. The other advantage of high band gap semiconductor is that it can withstand much high temperature. You can make a device that will match at 600 or 800 degrees Celsius, no problem. 1000 degrees Celsius probably still no problem. But then with your traditional semiconductor, temperature can be an issue. You have to go to high temperature. Okay? So there are advantages and disadvantages. So you can see that what is the purpose? Why do we have to play this game of controlling the sex? Okay? So that's the main topic. See it. Go back to my slide. I think this should work. Yeah. Okay, so with that, let's move on and give you some references. I think there are some additional references later on as well. So I'm using some of these. Again, some very, very basics for those who don't know, doesn't have the right background here. We know about vacancies and interstitial typical type of defects or defects in materials. By the way, besides point defects, there are a lot of other important defects in materials, which is dissipations, linear defects, two-dimensional defects, three-dimensional defects, and defects and so on. But yet, mixable flow, particularly mechanical defects, but point defects are sort of mapped to one or functional to one. And that's why I'm going to only limit my discussion to one. there are a lot of other defects that are relevant to results. We know point defects control many properties like fusion and electricity, thermoconductivity, ionic conductivity, even yield. So, yield strength of your material would depend on point defects. And then many other. So first I'm going to talk a little bit about thermodynamics of a sample equilibrated in an environment, because this controlled atmosphere processing will always require your sample equilibrating in some sort of environment where you can control the gas or oxygen partial pressure, etc. So that's your experiment. So there's that like showing that you have a sample output, which is your solvent, and interacting with the gas phase. And I'm going to talk about the equilibrium level of amount of point defects you create that is in equilibrium with the environment. Kind of scenario, and you will see that one of the conclusions will be that if you take your sample to high enough temperature, where you create a certain amount of vacancies that are equilibrated with the environment, meaning the oxygen partial pressure, the gas environment, and the temperature, the equilibrium amount of vacancies, chemical potential vacancy. That's thermodynamics out of the your sample will violate of that, meaning that you have created a state in terms of amount of point defects with kind of metastable defect state. Meaning that you heat treat the sample now, and the amount of vacancies you create will change. And eventually you will go to this sort of equilibrium number of vacancies. And we're showing that when it gets to that equilibrium level, the chemical potential, which is an important property of the solvent, chemical potential of those vacancies will stay. Okay? So that's the exercise that we do first. And you will see your familiar things that you have seen, thermodynamics, the internal energy of your solid phase. You can write it changing in the internal energy with du as TdS entropy minus dEV plus the chemical potential terms, because now you have an open system. You're exchanging gas between the solid and the gas phase. Okay? So whenever you have an open system, then you have to add this chemical potential terms to change the internal energy. You already know that. For example, if you didn't have an open system, if it's a closed system, you just have to deal with TdS times dD beta. The chemical potential terms. All right. Then you can turn around and you can express this in terms of change in entropy. And I'll talk about that next time. So you can rearrange this if you're interested in finding out what is the change in the entropy of your solid that is interacting with the gas phase. Similarly, you can write an equation for the gas phase. So this is for the solid phase, what is happening to your sample versus what is happening to the gas phase. And you will notice that when I write this for the gas phase, I write chemical potential for the components that is in the solid. And the vacancy term, so this is chemical potential of vacancy in the solid. That vacancy term is not relevant to the gas phase. And that's understood because you have sort of molecules in the gas phase, and if these molecules are interacting, then if you go to very high PO2, your oxygen will actually incorporate the solid as oxygen incrustation. If you go to very low PO2, oxygen will actually get out of your solvent and come to the gas phase. So that's the interaction. And that's how we create vacancy. That's VIO2 minus X. Vacancy of the oxygen subminus. But vacancy doesn't have any meaning. Does it? Vacancy is basically something is missing on the lattice side. Gas phase has no lattice. So that's why the vacancy term is not but the other terms. See, as I said, if you go and turn around and look at the change in entropy of the system, combined solid sample plus the environment. So this is the change in entropy for the solvent. It's the whole thing. And this is for the gas phase. Okay? So that's my total change of entropy during this interaction between the solid and the gas. And if you know so this is system sample plus the sound. You can say that this is your change of entropy of the universe meaning sample of the sound. And if you recall your second law of thermodynamics, for a system where you're looking at sample plus the sound, which is an isolated system, all the changes have to be zero. Internal energy, volume, change, the number of moles, etc. And as a consequence, you will see that the changes will have to be equal and opposite. And that makes sense intuitively because that's the exchange. Whatever is coming out of the solid is going into a gas phase, or whatever is being incorporated solid is coming from the gas phase. So that makes sense. So you can use those and go back and rewrite your, change in entropy of this isolated system, which is sample plus the sound. And you see now you get an equation that will look something like this. You can see this is going to illustrate when you take your sample is in equilibrium, there are three conditions that needs to be fulfilled. Thermal equilibrium means that temperature of the solid has to be equal to the temperature of the gas phase. That will give you thermal equilibrium. Mechanical equilibrium will come from the fact that pressure in the solvent will be equated to the pressure in the gas. That will give you mechanical equilibrium. If you know the chemical equilibrium, which is the third criterion, the chemical potential of a given component in the solvent has to be equal to chemical potential of the same component in the gas. Meaning, for example, chemical potential of oxygen in your TiO2 has to be equal to chemical potential of oxygen in gas. Otherwise, your sample has not attained equilibrium. So, by design, because of the criterion of equilibrium, this is going to be zero, this is going to be zero, this is going to be zero. But then you know that entropy change in an isolated system. In an isolated system, entropy actually reaches maximum. There is no further change. And the system is in equilibrium. So DS change in entropy has to be zero. So for this term to be zero, there is no other choice but to say that the chemical potential of vacancy in your solid has to be equal to zero. Otherwise, we are going to violate second law of thermodynamics. So that will illustrate here that if you ever create an equilibrium among the point defects in the solid, always remember the chemical potential associated with those vacancies will have to be equal to having non-zero. And unless you make a sample of metastatic defect, meaning you pick a high temperature, did something like quenching or something, and create an amount of defects that are not equilibrium amount of that defect concentration will change during application. in time. So how are we doing in time? Still. Okay, so that's an important thing that we learned. You probably know some of this, that you can do some simple calculation for concentration of defects in elemental crystals. All with elemental crystals like metals, single component, elemental technical, silver, aluminum, gold, etc. Things are simpler, and we can see that you can write the potential of the vacancy in that material, which is basically the molar Gibbs field. When you see Gibbs field with the bar, either on the top or on the bottom, molar, meaning Gibbs energy per mole. We know that Gibbs energy per mole is the chemical potential. You do know the that, right? The chemical potential will present how much the Gibbs energy of the system will change as you add or subtract one mole of the that's the chemical potential. So change in the Gibbs energy or mole of the material. Again, we know that that's related to enthalpy term and the entropic term. So the enthalpy associated with the vacancy, and the entropy you can write it in, you can expand them. You can write that you can say that the entropy is going to be, but the ideal solution model will be the entropy. Plus there will be an excess term. In general, you know that ideal solution will apply only to simple system where the vacancies and your species are non-defined. For example, I'll give you an example. Let's say if you are making copper nickel F, and it's basically mixing of the two liquids. If you look at from lattice quantum, you bring a nickel sitting next to a copper in the nanoform. And when you are bringing a nickel next to copper, copper does not even metal. So the system is non-interacting. It just, nickel is coming and finding an empty lattice site and fill it. If you have those kind of mixing, then you can apply your ideal solution, non-interacting. But in real life, most of the happen. So when you are mixing, sometimes something like our gold, for example, to mix non-ideal. So if you bring a copper next to a gold atom now has something to say. Either it will say, depending on the interaction, obviously, either gold will say, no, I don't like it, go to your buttons. So in that case, you will get trade segregation. So copper will stay with copper, gold will stay with gold, and you will get two trades. They will not mix. It will happen soon, some of the next one. Or, depending on the interaction, gold will say, oh, I like it. Please come and sit next to me. In that case, the solution alloy will be promoted. So there are depending on chemical interaction, either some system will want to mix, some will not want. But so that's the ideal term. It usually will come as Boltzmann constant logarithm of the concentration of vacancy, and then excess term. This is on top of IT. As I said, if you have an interactive system, there will be excess entropy related. So that's that. So you can, again, you can go back and write the chemical potential of vacancy in a solid phase, enthalpy terms, the excess entropy term, and this is the ideal. So I just added that. And you can, we already know that if you create the chemical, vacancy, equilibrium amount of vacancy, we know that second law of thermodynamics says that the chemical potential of the vacancy has to be equal to zero. There's no other. This is why I store that level first. Okay? So that's what I'm important. That potential is 0, so you can put this equal to 0, and you can actually solve for this fractional concentration of vacancy in the solid. By the way, this is same quantity as that. Since I'm using different sources, sometimes symbols are different. So this is same as that. And you can see that when you put this equal to 0, it will give you all this exponential term. It's solved. And it will come out to be that there is an enthalpic term, and the excess entropic term goes in here that I'm replacing as a constant A. Why? Because this term does not depend on temperature. So temperature dependence goes into the enthalpy term. So it looks like this concentration, vacancy concentration would be some temperature independent term and so-called thermally activated. And this delta H sub B, which is same as this quantity notation again, is represent enthalpy that you need to spend, enthalpy like thermal energy, to create them. This is very important for us. That will give you an idea of how easy or how difficult it will be to make defect solid. And we'll talk about this. Yeah. Okay, so I already talked about this. And if you take logarithm of that term, you will get entropic term will look like this. And the temperature term will go as 1 over T. So if you plot logarithm of vacancy concentration versus 1 over T, you get a straight line. That should look something like this. And from the slope of the line, you actually calculate this enthalpy for creation of vacancies. Very, very important for us. And this is what people do in the experiment. So they will actually take a sample, take it to different temperatures, get a straight line fit. You need at least 2 days to count and use the line. Because anybody can draw a straight line to drops. How good the straight line you have, to prove that you need more data, at least one more better, and the slope will give you the delta H. And if you're interested in the entropic term, you can calculate the H itself also. So you can get both the entropic term and the enthalpic term, but people are mostly interested in the enthalpic term, because that will tell you how high you have to take the sample, what temperature you have to take the sample. Okay, so this is still some basic, so how do we measure the vacancy? Again, you will see that in simple metals, it's easy. And as you go into ceramics and so on, it's a little bit more complex. In simple metals, you can outguess by simply measuring electrical conductivity. So let's say if you're interested in doing different aluminum, silver. So you just take a wire, thin wire of aluminum, silver. Now all you have to do is measure the electrical conductivity to begin. Such as pure aluminum, no defect. And then you heat up that aluminum sample to 700 degrees Celsius. Hold it there for some time to cool. And then after you press the sample, you can quench the thermal vacancy, which created that sample. And measure the electrical conductivity again. And keep doing it. Now we go to 800 degrees and 900 and measure the electrical conductivity. And from the change of the electrical conductivity at different temperatures, you can actually figure out the amount of vacancies that you are creating that silver or aluminum. So just to model this electrical resistivity without any defect. Plus, this is coming from data. And you introduce number of defects, and each defect will associate some electrical resistivity. So this is coming from the defect part. And then you can rearrange a number of defects. You can see that can be expressed as delta rho, changes of voltage, divided by the resistivity introduced by each defect. Normalization in that sense. And and then you can keep going. Math is simple. The definition of this fractional vacancy concentration is number of vacancy divided by the total number of sites, for example. And we know that this has to come in this form. There is a temperature independent part, as I showed you on the previous slide, and the temperature dependent part, that is the enthalpy. And then you will see that in that case the delta will change in the electrical resistivity can be still given by that enthalpy term, but this A will be renormalized, by certain amount, and some presenting a different A. This A has enthalpy. But this is still the important. So the now says that if you take, if you look at the change in the logarithm of that resistance, as you take that negative perspective, but here you should get this enthalpy. So in other words, if you plot logarithm of delta rho versus 1 over t, you should get a straight line. And the slope, this is the slope of the derivative is the slope. So the slope will give you the enthalpy that I talked about. But you can see that this term you are getting from the change in the electrical conductivity of the sun by measuring delta rho. This has been done for many methods. Here is some data for the gold, for example. You can see this open circles are the actual experimental data, and you can see it fits very, very nicely in a straight line way, and you calculate the slope. That will tell you what would be the enthalpy needed to create vacancy in gold. And I'll show you some numbers. Here are the numbers. So it's in kilojoule per mole. Does anyone know the conversion between kilojoule per mole to electron volt? It should come out to be very close to 1 electron volt. I think the conversion factor is 93 or something. I may be wrong, but we can look up. And my assumption is for most metals, so the water is about 1 electron. Okay, so, but for many of these metals, they have figured this out, delta H, simply by doing this electrical conductivity measurement changes that you see. So, there's another way, before I get there, you can actually look at the change in the volume of the system. You can see that total change in the volume of the system is given by change anticipated from thermal expansion. If you heat up the solid, the solid is going to expand, and you can figure that out, how much the volume will change because of thermal expansion. And there will be additional volume change due to defect. So this is defect related volume change. And this is thermal energy related. So basically add those two up, that gives you the total volume. And this volume, defect related volume change, if you normalize by the total volume of the example, can be related to this fractional vacancy concentration. And for an isotropic solvent, like a cubic glass, it can be approximated as 3 times change in dimension length, delta L over L, minus a term that introduces a change in the lattice current. So the quantity that you're looking for, this fractional vacancy concentration in your material, can be calculated or estimated by looking at the dimensional change of your sample, which you can easily measure. And people use for fancy measurement, they use the electrometer. So depending on how fancy it is, we'll measure very minuscule changes in dimension. So there are techniques to measure dimensional change, and then you can normalize by the original light. So that's easy. How can we measure this? Change in lattice parameter. If you have ever taken the X-ray diffraction class, as you create defects in your solid, what will happen to your X-ray peak position? It will shift. And from shift of the peaks in your X-ray diffraction, you can actually estimate the delta A, change in lattice parameter. So there are experimental ways of getting this from X-ray diffraction. This is, you know already that this thing. And this was really proposed by Southern Simons and Bubble. By the way, this works very well for elemental. But if you want to estimate vacancies in your ceramic sample using this approximation doesn't work very well. We'll give you some rough number, but not more. So you can see that this is the data for aluminum metal. And you can see on this axis what is being plotted is dimensional changes and or lattice parameter change as a function of temperature. And you can see that at low temperature they overlap on top of each other. And then as you go to 550 degrees or exceed 500 degrees Celsius, they are starting to diverge. So this one is the dimensional change, and the lower one is the lattice parameter. And you can see in this equation, the bigger the difference, that means higher the amount of vacancy. Okay? And that makes sense because it's showing that as you are going to higher and higher temperature, they are diverging more and more, because you're creating more and more vacancy. So this sort of technique, we estimate vacancy concentration, works very well for elemental lattice. And here's some more data. You can eventually, calculate the not only the vacancy concentration, but you can calculate the atomic term, you can calculate the enthalpy term, and this has been done in many of the metals. Yeah. This is metals that include this for all. So it's very reliable, very good data that we use for this sample. So you calculate this fractional vacancy concentration. It's just a number. So that many vacancies of the order of 10 to the negative 9. Very small. So it comes out to be 60 parts per billion. So out of 60, out of billion sites, 64 would be. And you would say, who thinks? Well, if you're trying to control property of that, there's one slightly improved there, depending on what property. If you want to convert that fractional concentration into real concentration, like number of vacancies per cubic centimeter, which is the density that calculation, then you can do that. We have to multiply this by Avogadro's number and the molecular volume. We have to look up molecular volume of aluminum and use Avogadro's number that are known. And if we do that for silver at 700,000, the number will come out to be 3.75 times 10 to the 15 vacancies per cubic centimeter. So think about it, although this number looks much bigger now. But you're talking about this vacancy concentration in 1 cubic centimeter per turn. Think about how many trillions of lattice sites it will come. It's still small quantity. Compare that quantity with, let's say, concentration of electrons in metals. Why metals are good electrical conductors? Because concentration of electrons in metals is very large. It's typically of the order 10 to the 22. Okay, 10 to the 22 conversation. So compared to that number, still 8 orders of magnitude low. So, and I think that there's a very selected. Okay, we stop here and then continue. I know that with technical talk, sometimes in music and art, you can get long talk because there's a lot of dance and entertainment and stuff. Technical talk that particularly involving some of bandits and all this, crystal lattice and so on. We're going to do that research. So it depends on you, but I can stop here or I can. Let's just stop here. I think we have absorbed quite a bit for today and we'll just keep going. Is this exciting or am I wasting your time? I think most of the things I talked about involve part of the. Okay. All right, same time tomorrow.